Okay, let's begin, everyone. Yeah, so you see, I not only provided the practice problem, the exam practice problem, but also listed here for your convenience, as good measures of communication of ideas and facilitation of learning, the sections, and my handwritten notes related to the problem statement, okay? Related to the practice problem. So that way you would find everything in one place. I'd like to begin to come back to problem 2 quickly, not entirely, but just mention to you 2 points. Some students asked me before exam 1, but I'd like to also mention this to everyone. First is the justification of the trial solution for the particular solution, right? Given this polynomial excitation. And the second is the question 7 in more detail. I did provide the answer in the review before. So suppose that you have this linear second order ODE, and it is excited, and A and B are some coefficients that you can find, right? In response to the previous questions, namely how to go from the double real root to the differential equation that I already showed. It's very simple. It's just lambda plus 1/2 y square equal to 0, and then from there you obtain the differential equation. I did that before, so I'm not going to redo that here. Here I want to focus on the excitation and how to obtain the particular solution, right? So d1 t, d2 t square, and with d1 equal to 2 and d2 equal to 4. So I just want to write here in more general form, right? So for the particular solution, of course, you use the same PDE, sorry, not PDE, ODE, but with y replaced by yp, right? Because before you get here, you would have the homogeneous problem, right? And the homogeneous problem is the same left-hand side, except that the right-hand side is 0. So this is a decomposition that everyone knows. Okay, and the solution is with the H subscript designating the homogeneous solution. Okay, and then when you add the two together, you get back the original ODE. Okay, so what I'm saying is that if you superpose or add the two equations together, then you would have YH plus, maybe let me write like this, plus YP and I can move the double prime out. And and the same for the first derivative. Okay, so this is the prime here. Perhaps it's better to make it clear. And so plus A, and then plus the same term, but without taking the derivative, and plus B, right? And equal to the right hand side. Okay, so the excitation is the same, and you can replace YH plus YP by Y. Okay, so Y equal to YH plus YP. So my remark today is concerning the search for the particular solution. Okay? And the question is, what would be the trial solution? And to answer the this question 2, and the hint, justify whether C1t plus C2t squared can be used as trial solution. Well, first the answer is that the complete trial solution should include all orders. So, okay, so that means that YP should be equal to C0 t to the power 0 plus C1 t to the power 1 plus C2 t to the power 2. Okay. Now to justify this, so you want to assume that you miss the first term. Okay, so assume that that's the hint. Okay, so assume that you did not have this term. Okay, what happened? Can you get the solution or not? Of course, you can guess that the answer is no, and why. So here is the justification. So if YP is equal to C1 T1 plus C2 T2, then YP prime would be, and now let me use this color here so that one can see clearly, and that would be C1, right? And let me write over here so that you can see the parallelism, and plus 2C2. Right, that's the first derivative, and the second derivative would be simply, I need to remove this one also. Okay, just 2C2t, and the second derivative would be simply without this term and without t, right? So now replacing the result into the left hand side, you would have 2C2. Okay, that's maybe let me write the left hand side so that one can follow. Okay, so this is the left hand side. And then we just put 2C2, that's YP double prime, right? And then plus A times YP prime, which is this one. And let me put parentheses in blue. And then plus B times yp, and that's this one, right? C1t times C2t squared, okay? And on the right hand side, you have the same excitation, which is this one. Okay, so you have 2 unknowns, but 3 equations. Okay, because this is you have you can think of this as zero times t to the power 0. Okay. All right. So now it's just a matter of equating terms with like powers, right? So for the term with t to the power 0, you would see that on the on the left hand side you would have 2c2, right? And then plus ac1. Okay, these are the 2 terms, and on the right hand side would be 0. Okay, and now for the term, let's say t squared, you have C2 on the left, and on the right you would have B2. Okay, and then for the t term, you have 2c2, 2ac2, and then plus bc1, right? This term here equal to d1. You know, I mean, in order, I could put something like this. We go from order T0, T1, and T2. So here you have 3 equations for 2 unknowns. Yes, Brennan?
T squared term, should be a b in front of C2?
Yeah, B. Yeah, B times C2. Yes, you're right. Yes, so that's a factor B here that I forgot. Yeah. So 3 equations, 2 unknowns. That's more than you can have, and therefore there would be some conflict if you try to solve. There should be some conflict there. Okay. It's something that will not match. For example, you can take the first 2 equations to solve for C1 and C2, and you will see that the result C2 will not satisfy the third equation. So that's how you justify that if you miss, okay, let's go back here. If you miss the term with order 0, things will not work out. All right. So that's how you justify. And I think that should be, I'll come back to question 7 when we have more time, okay? So now let me, I'll leave it there for now. And let me bring up, let's see here. So problem 4, I have already showed you how to do this, right? It was, let's go back here. Problem 4, I think I have written in my handwritten notes that I put here for you. You see here, meeting 42, where you read projection on cosine basis, right? See, there should be. I remember I did write by hand the formulas, the important formulas. Yeah, right here. These are the important formulas here. And yes, so here I did show to you how to obtain the expression for cosine square in terms of cosine, right? Just by using trigonometric identities, and then after that justify that this is indeed the Fourier series by using orthogonality. Okay, so this in this lecture notes here already. Yeah, and also as mentioned here, this is exam 2.2, problem 4. So please review this meeting. Okay, so let's check here. So question 1 is known. Question 2, develop into Fourier series, and the hint is to transform the function into cosine or sine. Okay, and let's see here. Let me go down here to review for you a little. Yeah, so down here is the Fourier coefficients, right? And you replace cosine square by the expression in terms of cosine, right? Cosine square is 1/2 of 1 plus cosine 2x. And then that has to be multiplied by cosine of 2nx. Remember, cosine square is an even function. So all of the coefficients for the sine terms would be 0, right? Because the sine terms are odd functions. So you only have the coefficient for a0 and an. Okay? And then you can for n greater than 1, so cosine of 2x times cosine of 2nx for n greater than 1 will be 0 because of orthogonality. And you can use the formula of the product of two cosines to verify if necessary. But in an exam, if you are running out of time, then you can appeal to orthogonality, and then later on when you have more time, you can expand out the integral. Okay? So, but manage your time, that's what I'm trying to say. So that you can do as many questions as possible. And yeah. Yeah, so this is essentially the orthogonality here. And so A0 is simply replacing cosine square by 1/2 of 1 plus cosine of 2x. Right? And then from there, the integral of cosine will be 0 from over the period. And so what's left is you have the coefficient 1/2 there. Okay. And so that's essentially just the first term. Okay. And for the Fourier series, the factor for cosine of 2x is also 1/2, and that's right here. Okay, that's the coefficient A1. So you have A0 and A1, and all the other coefficients will be 0. Okay, so once you have the Fourier series, the next question would be to apply that as excitation to this scalar ODE, right, with simple initial conditions, right? So the first question is to find the particular solution, okay? Now the particular solution you can split into two parts, as I mentioned before. Let's see, let me go back to this one. Okay. Maybe let me write over here. So so if you have something, what was the equation? Y double prime plus 9y. Okay. Y double prime plus 9y equal to cosine square x, right? And that, in terms of Fourier series, is 1/2 plus 1/2 of cosine of 2x. So again, the problem can be decomposed into the homogeneous part and the particular part. So the homogeneous part would be with the subscript h and with 0 on the right hand side, and the particular part is essentially the same as written up there, but with p as subscript. Right? So the homogeneous part is simple. Everyone knows how to do that. This is in the way you also know how to do this. It's just a matter of reviewing. Okay. For the constant, you can split this into two parts if you want to. If you don't want to do this all together, then you can split this problem here, the particular problem, into two parts. The first part would be with the constant excitation, in which it's easy to find the particular solution. And the second part is with the cosine, right? And so what I'm trying to say is that this the particular solution. Maybe let me write down here the particular problem. Two sub-problems. And that is the following. Right, and call this YP1. That's the first problem, first sub-problem, and the second sub-problem would be similar, but with the index 2, so YP2, and the excitation would be the next term, right? So when you add together, you get back the original problem, right? So the solution for for the first subproblem is simple, right? Because you just select a constant, right? So if yp1 is equal to 1 over 2 times 9, then you get 1 over 2, right? So that's simple. Okay, what I'm trying to say is that this one is simple. Is simply a constant where you have 9 also down here. Okay. So replacing in that simple. The second one, you need to remember that you want to, and this is I gave here in the daily lecture summary, a section related to that problem so that you can review, and that section 8a, right? Periodic function, Fourier series, superposition of particular solution for trigonometric functions. That's the one. So let's let's bring up quickly that section 8a, and there's also the videos there. But I just want to point out to you which page, or remind you which page, because I did show to you before. This part here, yeah, right here. Okay, so if the excitation was either cosine or sine function, then on the trial particular solution has to have both cosine and sine. Okay, this is also very similar to the polynomial case in the previous problem. Okay, you have to have a full set of powers of t. Here you need to have both cosine and sine, because when you take the derivative, cosine becomes sine, and then you take the second derivative, sine becomes cosine again. Okay, so in this problem here, the trial solution has to be of the form if you want, you can use the same unknown here, m and n. So that would be m cosine 2x plus n sine 2x. Okay. So when you differentiate and replace into the left-hand side and identify the coefficient on both sides, or by the way, remember that when on the right-hand side, think of this as follows: plus 0 times sine of 2x. Okay, very similar to the case of polynomials, right? So when you differentiate the trial solution and replace into the left-hand side and identify the coefficients of cosine of 2x, you get one equation. And identify the coefficient of sine of 2x, you get the second equation. So two equations for two unknowns, m and n. Okay? So that's how you would. So once you solve for m and n, then you get the particular solution. Okay? And let me go over here. So that's question 3. All right. Now, question 4 is simple, because that's just the homogeneous solution. Right? Okay, homogeneous solution is much simpler. What would be the trial solution for the homogeneous problem? Anyone remember? That leads to the characteristic equation. Maybe instead of answering this question, if I have time, I'll come back to problem 2, okay, to review for you. But let's see, I'm looking at the time to be sure. So essentially, maybe let me write over here. So you have something. So for the homogeneous solution here, for the homogeneous problem, right? The trial solution. The trial homogeneous solution. Is YH equal to e to the lambda x. Okay. And when you replace, oh, yeah, I keep thinking in terms of t, but here the independent variable is x, so e to the lambda x. So when you replace e to the lambda x into the homogeneous problem, then you get the characteristic equation, and then you can have two homogeneous solutions. Okay. Let's see. And then once you have the homogeneous solution, you can combine with a particular solution, right, to get the overall solution before you satisfy the initial condition. Keep that in mind. Okay. Let me use this opportunity to answer the problem 2, practice problem 2, question 7. Okay. So, because it's basically the same problem. Okay. So here exam practice 2. Question 7. Right. So basically, this is you know, you can think of a spring mass problem, right? When you have m here and k here, and this is much simpler than the 2 degrees of freedom problem that you did in the first half of the semester. In fact, this is a particular case, okay? And the you can think the displacement as d, right? And this is free vibration. You have the initial condition d at 0 equal to d0, d sub 0, and d prime at 0 equal to v sub 0, right? The initial velocity and initial displacement. Okay, so what is the equation of motion? You can do free body diagram and you can derive that would be md double prime plus kd, right, equal to 0. So this is this is the equation of motion plus these two initial conditions form the complete problem, right? And to solve this problem, this is, you see, this is a homogeneous second order differential equation. So the trial solution, let me note down here, is of the form that, you know, that's what Euler gave to us. Okay, that would be d equal to e lambda t. Right? And so when you differentiate twice and replace into the differential equation, that you have m lambda square, right, plus k times e lambda t equal to 0. So now what's the next important step? The next important step is to say that exponential of lambda t is never 0. So therefore, this term here, this factor here has to be equal to 0. Okay. This is the result, and therefore lambda squared is equal to minus k over n, which is negative, right? Okay, because k is positive, m is positive, so minus k over m is negative, and therefore lambda is plus or minus the imaginary number square root of k over n. Okay, and square root of k over n is usually given a symbol omega, which is the circular frequency. So lambda is plus or minus I omega. Okay, so therefore the solution D can be written as C1 E plus I omega x or t in this case, and plus C2. Let me move down so I have some space. Times the same factor but with the minus sign in the exponent. Okay, so this should be maybe put it in red so that catch your attention. Okay. And then through an argument in one of my section, you can convert this into cosine and sine using the Euler formula. Okay. So this you can write as A cosine omega t plus B sine omega t. Okay, that's the solution. And so with A and B, can be used to satisfy the initial condition. Okay, so A and B, once you replace the initial condition you can solve for A and B in terms of the initial condition. So let me recall the initial condition, which is up here. Right? You can solve for A and B. Okay, for example, the displacement at time 0 is d0, and when t equal to 0, this term cancel out. T equal to 0, cosine equal to 1, so A is exactly d0 immediately. So here you can write. Okay, and then for the velocity, you need to take the derivative, right? So that cosine becomes sine, and here you have cosine, but you have omega. So b times omega cosine of 0 is equal to 1, right? So therefore, v0 is equal to b times omega. Okay. So therefore, you can get b is v0 over omega. So how to answer? So that's the result that can be used to answer question 7 here. First, if you double the amplitude of the initial condition, meaning the initial displacement d0, okay, you can also double the velocity, but think about double the displacement only. Would the mass oscillate faster? Well, oscillation, number of oscillations per second is related to circular frequency, right? And the circular frequency, I just showed here, the circular frequency is only a function of the spring constant and the mass K over M, independent of the initial condition. Okay? So the number of oscillation is the same, even though you change the initial condition. Okay? For example, you pull the spring out even further before you release it, the number of oscillation remains identical, doesn't change. All right? So that's the answer. That's the complete justification for that answer for the first question. And now for the second question, would the mass move faster? Well, you know the velocity, if you look at the answer here, you know, you need to differentiate that, right? Which we did. Okay. What you notice is that when you differentiate the displacement to get the velocity, you have the omega moving out, but you see A and B is a function of the initial condition. So clearly, the velocity will depend on the initial condition. So if you pull out the spring, double the initial displacement of the spring, meaning double d0, the velocity will be affected. So the velocity is also increased by 2, particularly when the mass goes back to the original position. Okay, when you see here. Okay, this mass here will oscillate, and what I'm trying to say is that if you start initially and release it, then when it moves back to the initial position, the velocity will double when you double the initial displacement. Okay? And the justification is given in the result right here. Okay, right here. And the reason is because the coefficient A and B both depends on the initial displacement and initial velocity. Okay, so that's a complete justification. And by doing this question, I also show to you or review to you how to solve the homogeneous second order differential equation and how to use the trial solution to obtain the characteristic equation. Okay, and that essentially completes. I hope that completes this problem here. Right here. Before the computer goes out. This problem here, right? It's the same. Okay. This is problem 4. Whereas what I did just before I come back here was problem 2, question 7. All right? Okay. And now I have a few minutes left. How much time? I have 7 minutes. I have enough to make this comment. You know, this is problem 4 that all of you did. Remember that? Yeah, I think I need to run this again. Yeah, for some reason the smart ink refused to work. Let's see. Okay, I cannot write directly on the screen, but I can make comments. This is projecting logarithm of 1 plus x on the cosine function, cosine basis function, which I have already pointed out to you. here I just want to point out one thing, okay? That I noticed that the team made some students make a mistake, and this is okay, I need to look for that logarithm. Okay, here. You see, this is team 7 of fall 2000. Maybe I can use the mask. Okay, what you notice here is that this is the SI function. Some students just not really pay too attention and just copy the solution and think that SI stands for sine function and wrote in their report sine instead of SI. Now, SI with the S in capital letter and I is not a sine function, it's called the sine integral function. Okay? And this team 7 did mention that. They mention it right here. But for some reason, students only are so anxious to copy down the solution and misunderstood. They said here, SI is the sine integral. You can evaluate the sine integral with MATLAB also, but instead of doing that, this team used the MATLAB numerical integration to integrate. Okay. And they presented the result, and so some students skip all of this and just copy down their result and presented it. So skip the whole reasoning, so misunderstanding the result and skip the steps and then copy the result. So it's like you have a gap that you cannot bridge. Okay, so please be careful. I don't want to point out specifically which team, but I just want to really warn that the solution guide is there to help, but make an effort to really understand and not copying and paste. Okay, so very good. I think you can write a lecture summary. There's still 3 pages here: team 9, team 1, and team 3. 1, 3, I can bring to you. Team 3, team 3, and team 1. Team 1, right? Team 1, where's team 1? Oh, that's it. So let's say if you run out of time, you could make the answer.
Well, like minus the J plus, we had that.
For sure. Where do you
Well, we already know what X and created the entire
Yeah, like I said, on the other hand, if you have plenty of time, then you can write down what you want.
Right now. Is there a class? What? Is there a class?